Over the past century, physicists have been fascinated by the concept of black holes, with the idea growing in popularity around 1916. These cosmic anomalies are among the most enticing and mysterious phenomena we are familiar with. At the convergence of enormous gravitational forces and an unusual disappearance beyond our comprehension, a black hole, possibly weighing between 2 and 4 million times the mass of our Sun, continues to be an enigmatic presence. In spite of decades of intense research improving our understanding, black holes remain a mystery. From having very little knowledge to piecing together more information, recent discoveries, especially Michio Kaku's breakthrough, have revealed shocking insights into the interior of black holes. These findings may challenge long-held beliefs and provide new perspectives on the nature of these celestial bodies. This brand-new data opens the door to more in-depth investigations into what might not have been considered before. Now, come along with us as we move further into the intriguing universe of black holes and discover what is concealed within the vast and inspiring landscape of the cosmos. What exactly are black holes? To examine the most recent findings by Kaku, it is essential to revisit the basic comprehension of black holes. The vast majority of us have at least a general understanding of what a black hole is. However, there are still a few key elements that remain a mystery. In 1916, Albert Einstein's revolutionary theory of general relativity predicted the existence of black holes. At the time, the concept was purely theoretical. It wasn't until roughly 50 years later, in the 1960s, that evidence proving their existence was discovered. Studies of the bright star X1, a celestial body that emits X-rays, revealed that these X-rays were not just moving at random but were being pulled into an invisible, dense mass. This mass was later determined to be a black hole. This discovery altered how we perceived the cosmos. It was monumental because it demonstrated that black holes were not merely theoretical inventions of Einstein but real, elusive entities deserving of further investigation. As a result, scientists worldwide began a search to learn more about black holes. Their efforts led to the discovery that the Milky Way alone may contain approximately 100 million black holes. However, due to the difficulty in identifying them, this estimate remains broad. Scientists believe that these massive entities number in the millions and are hidden within our galaxy, making it even more important to comprehend them. The fundamental idea of gravity and black holes. Black holes exert an immense gravitational force on anything that enters their vicinity. The singularity is the point at which the known laws of physics break down. To put it simply, black holes function like enormous vacuum cleaners, pulling everything into their depths. One of the most frightening aspects of black holes is that if someone were to fall into one, they would be stretched and torn apart by extreme gravitational forces before reaching the point of total devastation, something best avoided. Despite being scattered throughout the universe, the nearest black hole is nearly 500 light-years away. While this is still a significant distance, its relative closeness raises valid questions. In 2021, scientists achieved a significant milestone by capturing the first clear image of a black hole, specifically the M87 black hole. This accomplishment was made possible by countless nights of observation and compiling data to form a single unified image. As more information was gathered, researchers determined that black holes have 3 distinct layers, contradicting the common misconception that they have no limits. 1. The event horizon. This is the boundary beyond which nothing can escape. Once something crosses this line, it is inevitably pulled toward the black hole. 2. The photon sphere. This is the region where light becomes trapped due to the immense gravitational forces. 3. The singularity. This is the final point where everything is compressed into an infinitely small space, tearing apart the very fabric of reality as we understand it. Even more fascinating is the fact that each black hole is unique. While they generally follow this 3-layer structure, their behavior can vary significantly, making them especially difficult to study. Since conventional scientific methods do not apply, researchers are forced to use indirect techniques, such as observing the radiation emitted or analyzing the gas and dust surrounding them. Challenges in black hole research. Directly inserting a probe into a black hole is an impossible task, as anything that passes through the event horizon is inevitably drawn toward the singularity and crushed into nothingness. Since such missions would ultimately fail, spending billions of dollars on direct exploration is not feasible. As a result, researchers investigate black holes from two perspectives: observation and theoretical modeling. Despite their three-dimensional nature, black holes challenge the very foundations of physics. No two black holes are identical. When studying them, scientists must account for the breakdown of current physics theories. The formation of black holes. Black holes are believed to form when massive stars collapse. As a star exhausts its fuel, it can no longer generate enough energy to counteract gravity. Eventually, the inward pull causes the star to collapse. If the star is sufficiently massive, this process continues until matter is compressed into a singularity. To gain a deeper understanding of black holes, NASA researchers have focused on studying the center of the universe, particularly the M87 galaxy. Observations revealed a massive whirlpool of hydrogen gas spinning at an incredible speed of 1.2 million miles per hour. The effect of centrifugal force should have caused this gas to disperse, yet it remained intact. This indicated the presence of an enormous object at the center, most likely a black hole with a mass 3 billion times greater than our Sun. Theoretical advances and wormholes. In 1963, New Zealand mathematician Roy Kerr applied Einstein's equations to describe a new type of black hole, one that rotates. Instead of collapsing into a single point, a rotating black hole forms a structure known as a thin ring. This rotating disk of matter, called the ergosphere, is essential to understanding how physical laws break down near black holes. Kerr's model also predicted the possibility of an Einstein-Rosen bridge, commonly known as a wormhole. This theoretical passage could provide a shortcut through spacetime, potentially connecting distant parts of the universe, or even parallel universes. Wormholes are essential to comprehend. The description of the concept of spacetime in the mind-boggling explanation of Michio Kaku's spacetime theory, proposed by Einstein, describes spacetime as a warped, four-dimensional fabric distorted by massive objects. This warping creates gravitational fields that influence the movement of other objects. Consider spacetime to be a piece of paper. When the paper is folded, it creates a shortcut between 2 points. This is a wormhole. The essence of a wormhole is that it provides a shortcut, allowing spacetime traversal that could virtually connect distant locations. Despite the fact that wormholes are a theoretical concept without direct evidence of their existence, they are a natural outcome of general relativity. However, wormholes are inherently unstable, meaning that even if they were constructed, they would collapse quickly. Despite this instability, the concept of a wormhole as a potential gateway to different areas of the universe, or even distinct locations in time, has fascinated physicists for a long time. One particular type of wormhole, known as the Einstein-Rosen bridge, or ER wormhole, has been a subject of great interest. Theoretically, this type of wormhole could connect two distant points in spacetime, possibly even linking different timelines or universes simultaneously. While the idea of using wormholes for time travel or interstellar travel is thrilling, there are numerous significant obstacles. Wormholes are expected to have extreme instability, intense radiation, and immense gravitational forces that would make traversing them nearly impossible. Critics argue that while Einstein's equations provide a useful framework for understanding wormholes, they do not account for quantum mechanics, the field that governs subatomic particles and radiation. To fully comprehend wormholes and black holes, a new theory is required, one that unifies gravity with quantum mechanics. This pursuit, often referred to as the theory of everything, has been a major goal for physicists. One promising candidate for this unifying theory is superstring theory, which asserts that subatomic particles are not point-like but rather tiny, vibrating strings. According to this theory, the fabric of the universe is made up of these strings. Not only does this theory explain gravity, but it also provides insight into the behavior of black holes and wormholes. Additionally, superstring theory requires the existence of extra dimensions of spacetime, which are so small that they remain undetectable with current technology. Despite the challenges in studying wormholes, black holes, and the fabric of spacetime, scientists remain engaged in exploring these concepts, as they have the potential to revolutionize our understanding of the universe. The search for a unifying theory, whether through superstring theory or other approaches, is an ongoing challenge. However, it holds the potential to reveal fundamental insights into the nature of reality itself. These hypotheses suggest that the universe consists of more than just the three usual dimensions of space and one of time. In fact, they imply the existence of additional dimensions that are so compact that they cannot be directly observed with today's technology. However, these hidden dimensions may hold the key to understanding phenomena such as black holes, dark matter, and dark energy, some of the greatest mysteries in modern physics. Superstring theory offers a remarkable depiction of the universe, claiming that all forces and matter arise from the vibrations of tiny strings. These strings can vibrate at different frequencies, much like guitar strings producing different musical notes. Each distinct vibration corresponds to a different fundamental particle. If validated, this theory could provide a comprehensive explanation of the fundamental forces of nature, including gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Additionally, it could offer solutions to some of physics' biggest questions, such as the nature of dark matter and dark energy, which together make up the vast majority of the universe's mass and energy yet remain largely mysterious. However, despite its elegance and potential, string theory remains unproven. One of the major challenges in testing the theory is that the additional dimensions it predicts are so minuscule that they are beyond the reach of current experimental techniques. To detect them, we would need instruments with unprecedented precision and sensitivity. Even then, the evidence might be indirect, making string theory difficult to test using traditional scientific methods. Nevertheless, its mathematical coherence and beauty make it one of the most compelling ideas in theoretical physics. At the same time, scientists continue exploring alternative approaches to understanding quantum gravity. Black holes, for example, provide another area of study that may help integrate quantum mechanics with gravitational theory, potentially leading to groundbreaking discoveries about the nature of the universe. The behavior of subatomic atoms, in accordance with the theory of general relativity, explains the behavior of massive objects such as planets. The hope is that, by studying stars and black holes, scientists can combine these two theories to acquire a more precise understanding of quantum gravity, how things work at a fundamental level, and, in turn, gain a better understanding of cosmic objects like black holes. Phenomena where quantum mechanics meet general relativity are particularly important when studying black holes. This is due to the extreme circumstances near the event horizon of a black hole, where gravity exerts a tremendous amount of force. Scientists seek a theory that can explain both relativistic and quantum effects, particularly how they actually affect the interior of a black hole. The singularity, one of the most perplexing and bizarre environments in the universe, is the point at which time and space become so distorted that the usual physical laws break down. Comprehending what takes place in such a region necessitates a theory that reconciles general relativity and quantum mechanics. This has resulted in the advancement of concepts like loop quantum gravity and other models of quantum gravity, which seek to address these contradictions and provide a more complete understanding of black holes. As we continue to explore the mysteries of black holes, one thing is certain: the more we learn, the more we realize how much remains to be discovered. Black holes are not just isolated regions of devastation. They are also locations of incredible potential and complexity. Some theorists propose that they may serve as entry points to other dimensions or hold the key to understanding fundamental aspects of space and time. Black holes continue to be an important field of study, and as our tools and theories evolve, so too will our comprehension of these mysterious objects. One of the upcoming major challenges will be to improve our approaches to observing and studying black holes. One of the most exciting innovations in recent years has been the observation of gravitational waves. Gravitational waves are fluctuations in spacetime caused by the rapid movement of massive objects, such as the merging of black holes. By detecting and analyzing these waves, scientists can study black holes and other celestial objects in ways that were previously unattainable. The identification of gravitational waves has already provided revolutionary insights into black hole mergers, and future experiments will likely yield even more information. Another promising area of study involves the use of advanced imaging and telescopic techniques. The Event Horizon Telescope (EHT), which produced the first-ever image of a black hole in the galaxy M87, is a prime example of how cutting-edge technology is shedding new light on these enigmatic phenomena. By combining data from multiple radio telescopes worldwide, the EHT was able to capture an image of a black hole's shadow, providing an unprecedented look into one of the universe's greatest mysteries. As technology continues to advance, we will likely gain even clearer views of black holes, along with additional insights into their role and behavior in the cosmos. Black hole research is not just about understanding these strange objects in isolation. It is also about grasping the fundamental workings of the universe. Black holes play a crucial role in our understanding of space-time, gravity, and the very nature of reality. Through their study, we are not only uncovering more about black holes themselves but also pushing the boundaries of the laws that govern the universe. Black hole research remains one of the most thrilling and challenging areas of contemporary physics. With each new discovery, we move closer to deciphering the mysteries of these cosmic giants, whether through gravitational wave studies, technological advancements in imaging, or the development of new theories. Black holes continue to capture the imagination of both scientists and the public. As we investigate these extreme and mysterious objects, we are compelled to answer fundamental questions about the nature of space-time and existence itself. In doing so, we may be approaching the resolution of some of the universe's most profound secrets, perhaps even finding answers to questions that have eluded humanity for millennia.